Good morning. Welcome back to Mindray live session. Hope you have enjoyed our topic yesterday. Today we will be talking about protective ventilation during anesthesia. Postoperative pulmonary complications can lead to serious side effects and longer hospital stay. For obese patients and patients with other diseases, the risk is even higher. Because of this, we are using various lung protective approaches. So what role does transpulmonary pressure monitoring play in this regard? Mr. K. Krueger, Ventilation Business Manager from Mindray Europe, is going to give his speech. Welcome, K.
Hello, my name is Kai Krueger. I'm the European Ventilation Business Manager, Mindray Medical. Today I'm going to talk about transpulmonary pressure monitoring. First, I would like to share some interesting facts about trumpet players. Trumpet players can achieve extremely high respiratory pressures when they're playing their instrument. As you can see from the study, the expiratory airway pressures can exceed 300 centimeters of water even. Under normal conditions, this would be lethal. How can they sustain this? Trumpet players are using their respiratory muscles, the diaphragm, the intercostillary muscles, the respiratory muscles to constrain their lung compliance, and with that achieve a low transpulmonary pressure that is protecting the lung. How can we use this concept clinically? The expert opinion, as you can see here, says to consider esophageal pressure measurement during ARDS treatment. This can be done by technology. What is the basic concept of transpulmonary pressure? Transpulmonary pressure actually is the difference between the alveolar pressure and the pleural pressure. Alveolar pressure, for practicality reasons, is set equal to the airway pressure. Airway pressures can be measured by the ventilators directly and easily. The pleural pressure is very difficult to measure directly, and therefore it's set equal to the esophageal pressure. Esophageal pressure, the correct value. How do we measure esophageal pressure? As you see here, the balloon is placed in the lower third part of the esophagus, just right above the diaphragm, in the height of the lung. Is that equal to the pleural pressure? No, it's not. The pleural pressure varies a lot in the lung. The gravitation increases esophageal pressure and also pleural pressures in the lower parts of the lung. So we have different pleural pressure in the dependent and in the non-dependent parts of the lung. The esophageal pressure can, of course, not reflect those differences, but it is the easiest and probably most accurate way to show sort of a global pleural pressure that can be used for guiding mechanical ventilation. In 2008, Daniel Tamor et al. Published mechanical ventilation guided by esophageal pressure in acute lung injury. They found that oxygenation and respiratory system compliance can improve significantly if an esophageal pressure guided protocol is used, whereas the conventional treatment with the ARDS net table for guiding PEEP in acute lung injury and ARDS. As you can see on the right-hand side, the goal was to achieve a positive esophageal or transpulmonary pressure and expiratory pressure, whereas in the control group, the end expiratory transpulmonary pressures were quite often slightly negative. Negative end expiratory transpulmonary pressures are leading to de-recruitment of parts of the lung and maybe cycling collapse. Another interesting finding of this work was that the variety of the settings was much wider with the esophageal pressure guided protocol. So it seems that esophageal pressure guided ventilation applies more to the physiological differences in the patients, whereas a standard protocol would not be able to reflect the differences in the physiological settings. ARDS. On the left-hand side, we can see a normal lung. The end expiratory lung volume in normal lungs appears to be normal, and the strain during mechanical ventilation is normal. On the right-hand side, we have a typical ARDS lung, where we have huge differences between the dependent and non-dependent parts of the lung. So you see on the upper part, we have recruited lung volume. On the lower part, we have non-recruited lung volume atelectasis that leads to what is called the baby lung in ARDS. In those conditions, the end expiratory lung volume is low and the strain is high. Gattinoni et al. Actually also published a couple of years ago that in healthy lung, mechanical ventilation becomes injurious and lethal when the stress and strain are at around the total lung capacity. Therefore, unphysiological stress and strain occurs in humans when tidal transpulmonary pressures are greater than 22 to 23 centimeters of water. Clinically, that means that the plug group recommends not to exceed transpulmonary delta pressures of 15 to 20 centimeters of water in healthy patients and 10 to 12 centimeters of water in ARDS patients. The delta pressure, the change pressure, the difference between end expiratory and inspiratory transpulmonary pressure is also called the transpulmonary driving pressure. Earlier, I've explained that adjusting PEEP to maintain positive end expiratory transpulmonary pressure can significantly improve oxygenation and compliance. How to measure transpulmonary pressure? As explained before, we need to place the esophageal balloon. It needs to be inflated. Correct placement and proper inflation is quite important for the accuracy of the measurement. The esophageal balloon is then connected to the mechanical ventilator. And of course, the ventilator can also measure the airway pressures and with that show transpulmonary pressure directly. This can be shown graphically or in absolute values. Here we have two examples. On the left-hand side, you see a ventilation setting with a PEEP of 0 and inspiratory airway pressure of around 17 centimeters of water. The resulting in measured transpulmonary pressure in the graph shows that during end expiration, it's highly negative, here minus 18 centimeters of water. On the right-hand side, you see adjusted settings in order to achieve a positive transpulmonary and expiratory pressure. Those adjusted settings mean that the PEEP was increased, in this case to around about 12 centimeters of water. That also led to an increased and inspiratory pressure that was around 27 centimeters of water. The and inspiratory transpulmonary pressure resulting from these settings did not exceed 13 centimeters of water. And also the delta pressure, the transpulmonary driving pressure, did not exceed 13 centimeters of water and could be considered uninjurious. We also have the option to directly measure the parameters. On the bottom, you see 3 parameters that can be shown. On the left, you see PTPI, the inspiratory transpulmonary pressure, PTPE, the expiratory transpulmonary pressure, and delta PTP, the driving transpulmonary pressure. Thanks a lot for your attention.
Thank you, Kay. Now let's move on to talk about adaptive minute ventilation, AMV. With proper application, AMV is believed to be able to support customized ventilation settings for individual patients during anesthesia. Our second speaker, Mr. Ludwik Ray, Anesthesia and Ventilation Product Manager from Mindray Europe, is going to elaborate the application of AMV. You are welcome to start, Ludwik.
Good morning, ladies and gentlemen. My name is Ludwik Ray and I work for Mindray as an Anesthesia and Ventilation Product Manager in Europe. I would like to explain you the basics of adaptive minute ventilation that we offer in our ventilators, as well as in recently launched anesthesia device A8 and A9. First of all, let's see what is the general concept behind AMV and who is the inventor of that concept. AMV is based on closed-loop concept. The ventilator uses the feedback signal that comes from measured parameters to adjust the settings in a way to reach the final output. Several parameters can be adjusted automatically under this concept. That's the main benefit of the AMV. There are several closed-loop system modes on the market. However, usually they are only dedicated for a specific period of the ventilation therapy, controlled or spontaneous breathing. AMV is the closed-loop system mode with most extensive period, meaning that it can be used during all 3 types of therapeutic periods. Please note that AMV, ASV, and AVM are essentially the same modes. The operation principle is similar. However, each manufacturer called it differently. The principles were established by Professor Tehrani, who invented the mode based on the idea of Otis formula in 1988 in the US. The source of the AMV mode is based on the Professor Tehrani genius invention. The adaptive ventilation mode was first in commercial use in Europe in 1998 and then in the United States in 2007. Now, already after 20 years of patent protection, the Mindray team developed the AMV mode based as well as on customer needs. AMV is pretty well known from the use in intensive care units. It gives the physician possibility to use the automated control. Recently in Mindray, we have implemented AMV as well in our newest anesthesia platform, A8 and A9. That's the first time when AMV is available in anesthesia device. We are the only producer that offers it as an option. What is the principle of the AMV? Actually, the adjustment of the ventilator is a challenge for many people who are not familiar with the device. The idea behind the AMV model is to free the doctors to think only about the ventilation and oxygenation goals, while leaving the details adjustments to the ventilator. On this slide, you can see with red color all the steps that are done by ventilator and controlled by intelligent algorithms, basing on monitored parameters. In these steps, no human intervention is required. Patient is ventilated on AMV mode, where only percentage of target minute volume and PEEP and FiO2 are set by the operator. All the other parameters are automatically adjusted by ventilator. In behind the AMV, ventilator is switching the modes to adjust the current setting optimally for patient status. His spontaneous effort, from no effort with the PRVC mode, through the partial triggering, where PRVC with volume support is used, to totally spontaneous breathing when only volume support is needed. The main goal of AMV is to minimize the work of breathing for a patient. That makes the biggest comfort for the patient actually. It is based on Otis formula, and as a result of the calculation, the optimal respiratory rate is set. On this slide, you can see all the Otis equation. The target tidal volume is reached based on desired minute volume divided by respiratory rate. Everything is with the smallest work of breathing as possible. Both in ICU ventilators and anesthesia devices, the procedure looks similar. While activating the AMV mode, it is necessary to be sure that patient data is fulfilled correctly or adjusted at that very moment. By proper sex and height choice, the system will calculate the ideal body weight. The corresponding minute volume will be proposed, and the only thing we need to set is the percentage of the minute volume we want to reach and the PEEP and the FiO2. AMV is controlled by protective measures as well. There is double level of safety ranges. That's the first one is the internal safety range, and all the borders of these ranges you can see on the right side of the slide. Tidal volume and respiratory rate, upper and lower limits are fully covered. And the second level of safety ranges correspond to the pressure and volume alarm limits. By all of these, we can be sure that the AMV is safe and will not cause barotrauma or volutrauma or come with the patient into the apnea. We smoothly go into the third part of the presentation, where I will list the most important parameters that need to be set at the beginning of use of AMV mode. First of all, while setting the AMV, it is important to give the height and sex of the patient that correspond to the ideal body weight. Now, just a small reminder, why height of the patient and ideal body weight is taken to further calculations? As you can see on the slide, only because the real weight doesn't correspond to the size of the lungs. Being heavier doesn't mean our lungs grow. They are the same size as previously. What's more, obese patients usually need more PEEP to keep the lung open, as the weight of the thorax itself squeezes the lungs much more. The formula for calculating the ideal weight of Mindray's ventilator and anesthesia device comes from the official website of ERDS.net, which is currently the most widely used formula in clinical research worldwide. However, the algorithm of the AMV mode is optimized on the basis of the Radford nomogram. In this table, you can see the initial settings of the AMV mode. Everything that is with the gray color needs to be adjusted by physician. All the other parameters are done automatically by algorithm. What happens after starting the AMV? Always at the beginning of the AMV mode operation, the system does 3 test breaths that allows to understand the status of the lung and the patient. Then, depending on the patient activity, the ventilation is controlled by ventilator or supported according to the patient efforts. Parameters like respiratory rate and pressure are adjusted automatically to ensure the desired output with the minimal work of breathing. This screenshot that we see now on the slide comes from the Mindray ICU ventilator. On the left upper corner, we can see the graphical display of AMV, so-called AMV site. In anesthesia devices, the A8 and A9, we have classic view with all necessary parameters displayed, but with no need for graphical display there. What are the advantages and challenges by using the AMV? At the operating theater, the AMV can be used successfully for trauma patients, where we need to really focus on the patient stability than at sophisticated anesthesia methods. Or during the neurosurgery procedures. AMV can be also used for weaning the patient from the ventilator, comfortable way to go through all the ventilation therapy. In the bullet points, the automatic switch of ventilation that improves patients' comfort and reduce the operator's workload. That is what the AMV is. However, there are also some challenges. So-called closed-loop ventilation, like AMV is still not standard request for ICU and ORs. Many physicians still didn't have an opportunity to work with this type of ventilation mode. Some does not use it because they want to have the total control on the ventilation therapy. Others are not familiar enough to see the benefits that are coming from the AMV. The most important is that the AMV allows to minimize the human intervention as well as possible errors during the procedure. AMV also doesn't require hours of training. It's also a good tool for hospitals with less medical staff when time per patient is quite limited. The level of care is standardized and based on transparent criteria, and that makes the AMV a good mode to trust and use. That's the end of my presentation for today. Thank you. Bye-bye.
Thanks to our two experts for sharing their knowledge of lung protection. And thank you to all of our attendees today. Don't forget that tomorrow at the same time, we will be having a special guest speaker, Professor Jean-Florian Huer from Augusta Clinics Bochum, to share his experience around transpulmonary pressure monitoring. See you then. Thank you.